Okay, we're very happy to have Vladimir Kanovei from IITP to talk about the significance of parameters in the comprehension and choice schemata for second-order arithmetic. Go ahead, Vladimir.
Thank you very much. Can I ask a question? What is MOPA?
Models of Peano Arithmetic.
Oh, okay. So it's significance of parameters in comprehension and choice schemes in this PA. This is just to recall that parameters are free variables in different axiom schemata. Let me just define for the sake of this talk that asterisk will mean parameter-free subscheme of any considered scheme. This begins with Kreisel, who was one of first students of subsystems of Peano arithmetic. And he was probably first who paid attention to the role of parameters. So this is just a citation from one of his papers. So he says that it's natural to study details such as the effect of parameters. So the talk is about the effect of parameters in the schemata of comprehension and choice in second-order arithmetic. Just some introduction. What is the second-order Peano arithmetic in this talk? That is two sorts of variables for natural numbers and for sets of natural numbers. And this theory contains, just as usual, Peano's axioms for numbers. Then induction comes as a scheme as well. It's not plausible in this case to add induction as one sentence, because in the absence of full comprehension, this may not reflect what we need from induction. And comprehension as usual. And now we can see difference between parameter forms, general form and parameter-free form. Induction will come with parameters. So it's can be also interesting to investigate the role of parameters in the induction schema, but not for this talk. So that's CA star, just as I said before, is parameter-free subscheme. That is, this formula phi cannot contain any free variable other than k. And accordingly, PA second star is the subsystem in which K star instead of CA. So star always means parameter-free form. So the main question is, of course, is PA star strictly weaker than just PA second? This depends on what do we mean exactly by comparison of strength. If we look at this from the point of view of consistency, then the answer is negative. That is, both theories are equiconsistent. This is, it seems that the earliest result, the earliest source of this result is a paper by Harvey Friedman, who established that PA and PA star are really equiconsistent. What is the method? We just try to argue in PA star. We just try to just to run Gödel constructive hierarchy as long as we can. And so this is a parameter-free construction, of course, and it is legitimately defined until some ordinal, or it really extends through all countable ordinals. But anyway, this is parameter-free definable construction, and we prove the full comprehension inside it. Well, because it happens that all elements of this construction are parameter-free definable. So there is just all parameters are just eliminated. Well, it is very just very surface look. There are some problems just with this proof and some extra arguments, but more or less this is just how it looks like at the first look. But this talk is devoted to another question. This is the problem between these two theories in the frameworks of the deductive strength. That is, does the full form prove more sentences than the parameter-free subtheory? And now we find that yes, it's really strictly weaker. That is, I mean, parameter-free form is really strictly weaker. It proves less amount of sentences than the full second-order Peano. So this is the first result. Well, in fact, what happens? The parameter-free Peano even does not prove that every set has its complement, which is a just very elementary, maybe most elementary form of comprehension. This is a actually simple result and simple model to prove this. So we begin with a constructive universe. The method uses the construction involves forcing. We consider generic extension by adjoining a Cohen generic sequence of sets of integers. And in this model, we define a set X, which consists first of all constructible reals. And second, it contains just this sequence of new Cohen generic reals. Just we adjoin only these reals and nothing more. We don't adjoin their complements, don't adjoin their different other combinations, nothing. Only these reals as such. And this X, so X is a collection of sets of integers. It happens to be just omega model of the parameter free P, in which these new sets do not have their complement. So therefore, the full CA fails. This is easy. More difficult part is that the parameter free comprehension still holds. That is, the idea is that the new reals, we cannot nail any new real by any parameter free definition. They really look very much like each other. So the sequence is sort of quite obscure one. We cannot nail any single of them, and therefore, moreover, we can't nail just any other possible violation of parameter free comprehension. Just technically, it's based on rather standard fortune permutation arguments of the coin fortune. Well, this is first result. And second result is, so this is conclusion. A star doesn't prove a very simple instance, not consequence of the full comprehension.
Vladimir, I apologize. It's difficult to ask questions online. I never know how to do it, but is it okay to ask questions? So at least you know that someone's listening. Maybe you will comment on this a little later. But what is the strength of this statement that every set has a complement? What happens when you add it to PA star 2?
Let me just go to the next page. Maybe.
Right. Okay.
Maybe. Well, I'm sorry. I am a little bit not fluent in English, which is not my mother tongue, and I did not have much practice the last 5 years, so I just apologize, because I apologize for my for in this oral exchange, that I just like that whoever wants to ask me something, be it in some slow way and in some kind of international English. Sorry about it.
No, it was perfectly okay. And sorry if we'll try. I'll try if I have any other questions to. I will try if I have any other questions to ask.
Thank you very much. Well, this is second theorem. Look, even if we adjoin sigma 1,2 comprehension to the parameter free form, so we adjoin comprehension for sigma 1,2 formulas with parameters. This definitely covers that formula which corresponds to taking the complement. It includes also all first order formulas. That is, with any combination of quantifiers over natural numbers. And this includes also the case of one quantifier over reals. So therefore, it includes like most of schemes normally considered for those who really are interested and who studies sub-schemes of second-order PA. So this is very strong sub-theory of the second-order PA. And even this strong subtheory somehow fails to prove certain instance of the full comprehension. Of course, this instance has to be more complex than sigma 1, 2. Actually, it will happen to be sigma 1, 4. Well, so this is second result, and it's much more involved. Let me just sketch the construction of a model which proves this theorem. Well, first it involves what I call basic model, and then certain submodel of the basic model. So we begin with constructive union. Then, well, the technical instrument is a combination of product and iterated Sachs function. So how it works? Well, consider index set. It is just a set of finite strings of countable ordinals, not including the empty string. Just tuples of countable ordinals. Well, we define this in A, so omega 1 is omega 1A. And then an array of generic reals which are indexed by tuples from this index set. And it is arranged that each S, if we take an index S from I and extend it by one more element, alpha is a countable ordinal. This B as extended by alpha is subgeneric over L of B sub S. Of course, there are some product forcing requirements which I do not consider explicitly. Well, and B sub empty tuple will be just empty set to complete the picture. Now the whole array of these reals, vector B, and generic extension by this array, I call it the basic model. Well, sometimes this sort of extension is called arboreal iteration because it's not a usual linear portion iteration, but rather it's arboreal because this structure of iteration is tree now. Index set I is a tree, not a linear order as in more common iteration. It's arboreal. Well, first of all, just two questions now. First, what is the portion itself for this index set for this extension? And second, how we process further. So first of all, about portion. Well, we can proceed just strictly following the usual machinery of iterated portion. But in this case, fortunately, there is some kind of geometric approach to this portion, which does not refer at all to the whole the idea of iteration as itself. So let me just explain the definition. So P deals with the portion. And let me define this set P first. Consider just arbitrary countable initial segment of this index set. It's psi, any countable initial segment. Secondly, power set of omega we consider just identified with 2 to omega Cantor space. So it becomes Polish compact space, and the product of psi copies of it is also Polish compact space. Now the key definition. Consider some kind of homeomorphism from this P of omega to psi into itself. Homeomorphism by compactness is just a one-one continuous function, but not necessarily onto. I call it projection keeping if it kind of honors the quality of projections. That is, take any initial subsegment eta and 2 elements, 2 points in this space. Then what is the requirement? If their projections onto this initial segment are equal if and only if projections of their images onto the same initial segment are also equal. And I call this sort of maps projection keeping homeomorphisms. And if H is such, then we consider its image, just the image of the whole space, which is product of many Cantor spaces. So it's a closed set. Now, portion itself, it consists of all such sets X sub H, in which first psi is arbitrary countable initial segment, and second H is arbitrary projection keeping homomorphism. And for this X sub H, just let the dimension of it be psi. This is not a sort of topological dimension, but rather kind of structure dimension. All of them are 0-dimensional, of course. And the order. So stronger means that it has a bigger dimension, but in that dimension it is slimmer. That is the dimension. First of all, smaller one means stronger. This is one of 2 possible approaches to portions, and I take this approach. Smaller means stronger. So it's stronger if X is stronger. If its dimension is bigger, that it simply includes the dimension of Y. And when we restrict this stronger one onto the smaller dimension, then it will be slimmer So this means stronger. So we just extend dimension, but make it slimmer in just previous dimension. So this is complete definition of the quotient. Well, it is called sometimes generalized, sometimes arboreal iteration of the Sachs quotient. Well, so this one really, just I come back to the previous slide, it really produces such a system, such an array of reals, indexed by indices from this set I. So each next one is sub-generic over the previous one. And additionally, the bottom one is an empty set. Just only to say that if the index is one element, then it is simply Sachs over the constructible universe. The whole array of them and the extension of L by this array, vector B. It's a basic model, a Borel iteration. So let's go ahead. And the principal technical instrument then is the lemma called strict successor lemma. What does it say? Take any index. Then, number one, for any ordinal, so we can adjoin the ordinal to the index and we get a bigger index. So the corresponding real B is then a strict successor of B sub S in the sense that it's strictly smaller, strictly the one which the standard index is strictly larger in the Gödel sense. And moreover, if any real, right, is strictly smaller than this B sub S extended by lemma, then it is non-strictly smaller than B with the original index. So you can say that the Gödel cone of this B sub S gamma consists of the Gödel cone of S plus the only one element B sub S gamma itself. I call it strict successor. So each real with next index is just a strict successor of the real with previous index. This is first. And second, just the other way around. If some real in the extension is a strict successor of BS, then it is just essentially one of B's with the successor, with a successor index. It just we can summarize this that the being strict successor in the Gödel order sense is just the same as being the strict successor in the index sense. This is just the main tool of any investigation, any definability investigation for such a model. Well, so this is about basic model. Now about the submodel. Now, in this extension by vector B, we consider the following set. First of all, we consider all reals with just one element indices, one term indices. So just the bottom level. Secondly, we consider we add a join all reals indexed by just ordinal extended by any finite sequence of zeros. So there is still a finite string tuple that begins with arbitrary gamma, and then only zeros. And plus, this is most important, reals whose indices are like this, just any ordinal, any string of zeros, and 1. But we are joined this real only when n, this n, the number of zeros, belongs to the real which does not participate here. It is the real b, gamma 1. I will show a picture just at the next slide. So W is a certain set of reals. And now we just consider the Gödel closure of, sorry, this is Z and should be W. So this is W. Gödel's closure with finite support, all reals in this model. That is not a Zermelo-Frenkel model, of course. So, okay, but we claim that X proves this theorem too. So we have to prove that it models parameter free PA plus comprehension of sigma 1, 2 formulas with parameters, but fails to prove certain instance of the full comprehension, more complex than sigma 1, 2, 4. Now let me show how the definition of the W looks graphically, so to speak. So first, let me start just with the 0 index ordinal equal to 0, and then we just adjoin the whole branch of reals indexed by only tuples of zeros of different length. Blue will be the structural success, so to speak. That is, it means that each higher one will be either strict successor of the previous one. And this B0 is the bottom. This is simply a strict extension of the empty set, which is not here. So this is just one branch. All right. So then there is a real, consider this real which is not in this branch. That is v sub 0, 1. Say, just for the sake of this picture, this set contains numbers 2, 4, 6, and some more numbers probably. Not necessarily all even ones, just what else, maybe 7, 11, no matter. Then what we add else? Look, we adjoin reals. We just, you know, make branching at certain levels. Namely, at which levels? At levels which are present in this set B01. That is at second level, just this upper index 2. Then level 3 we miss. Level number 4, because the 4, then B0, 4 zeros, and 1 is the index. 0, 6 zeros, and 1. So just to conclude, we install branching at exactly those levels which belong to this red set, V0 sub 1. And the red set is not, will not enter the model. We just keep it aside. Look now at, so assume that this is really just take a Gödel's closure of all of them with finite support. And let's have a look at this model. Well, the red real does not belong because we do not include it just explicitly. However, we can look at the structure of this structure of degrees of constructibility, and using that theorem about strict extension, we can just analytically define at which levels we have branching, right? And by this definition, we can define B sub 01. Therefore, we have a violation of certain complicated instance of comprehension axiom, which says, well, the set, the collection of all ends at which level we have branching has to be a set. So it is not a set in this model. But what is wrong with such a model? So CA is violated. But it happens that parameter-free CA is also violated. Why? Because this is the only one such a branch in this model. So we can argue like this. Look, take this only branch, just go to the bottom of it. And now, so this is still definable, right? Go to the bottom of it, just whatever you have at the bottom, then go up and look at those levels in which you have branching, and consider a collection of all corresponding ends. And this will be just, on the one hand, it is equal to this set V0 sub 1, but this set does not exist in this model. So we have parameter-free violation, which is not good, which is not what we want. So how to improve this? We have to obscure this thing, that is not to be able to really choose, not to be able to really say, just take the only branch which looks like this, go to the bottom of it, and have this everything in definable way. So how to do this? We just really multiply this construction, just make it just omega 1 wide, so to speak. So, namely, take the next successor real B1. It again has its red extension B sub 1 by 1. It has also its blue extension, just a long omega long branch of the reals, these indices 1 and a number of zeros. And at some levels, it has also branching. At which levels? At those levels which are present in this red set, which we do not include. Then just take the next branch like this, and so on and so on. Just omega 1 long, omega 1 wide, rather construction of the sort. Now you see each red real, say B11, to define it in this wide extension, we need to refer to B1. That is, we have to refer to parameter. And we cannot nail any parameter, any particular B from this 0 level, B0, B1, B2, B3. From them, we cannot define any real by a parameter-free formula. And actually, in this construction, we can check that really the parameter-free comprehension holds. Okay, to conclude, I just reproduce once again the collection of all these reals, which we include into the model. Yes, then X is a Gödel's closure of W with finite support. And well, the set X proves out there, namely parameter-free comprehension holds by the Fortune permutation technique. Then comprehension for sigma 1,2 formulas holds by the Schoenfeld absoluteness, and the sets B sub gamma 1, any gamma counter-doctrinal do not belong by construction. And on the other hand, each such a set is definable in X. This B gamma as the only parameter of the definition. So by means of lemma of strict successors, thus the full comprehension fails in this X, in this model. Well, so this is the sketch of this construction. And as I said, comprehension, if we just analyze the formula that has to be used to define this red B sub gamma 1, then it will be sigma 1 4. Well, and now problem which arises from this theorem. You can, in general, one can formulate it like this: prove that K second is not finally axiomatizable over the parameter free K. More specific form. If they are joined to the parameter free K, comprehension for sigma 1n, then still you so if they are joined to parameter free K, sigma 1 comprehension, these parameters, then it will not prove the full comprehension at the next level, the level n plus 1. This can be a very complex problem, but at least this theorem somehow partially handles the case when n is equal to 2. But the counterexample is sigma 1 4, not sigma 1 3. Well, quite recently, Vika proved really fully fixed this case by just towards sigma 1 3 counterexample, but using the different portion, more complicated portion. And well, general cases still remains work in progress. Hopefully, it will converge in a proof which works for every n, for any n. Well, I just like to finish it within an hour, so let me just very briefly consider some results about axiom of choice, countable choice, and dependent choice. This is well-known schemata. Well, AC star parameter free subscheme, and there is no need for DC because it's known that parameter free dependent choice somehow is equivalent to the full dependent choice. But, well, classical models, Levy model, in which this count of choice fails, it's a model called Levy collapse. So we need to make all cardinals below Aleph omega countable. So in this model, Aleph 1 is Aleph omega L. And this is actually Levy result. Well, then later, Guziski model of PA plus parameter-free choice, but not the general choice. It's also a model made by Levy collapse, but a longer collapse below Aleph omega 1. Well, we can consider as a shortcoming of these models that they use uncountable cardinals. So we cannot, we cannot run proofs like this. We cannot define these models, cannot even think about this in the frameworks of Peano second itself. We need much bigger part of Zermelo-Frenkel. But fortunately, we can define models of the same theories without cardinal collapse. So just once again, with the help of the basic model, which I considered in this talk. So Peano plus the negation of parameter free choice, Peano plus parameter free, but negation of full, and parameter at PA plus full count of choice, but not dependent choice, just higher, just 3 successive steps, so to speak. Well, once again, it's some models of the same basic model, L of vector B. Index set. Now, just consider certain initial segments of this index set. Namely, in this case, all countable initial segments in L, which are of finite height. So the segment can be wide, countably wide, but only finitely high, right? And define W. We just consider the set of all restrictions of this vector B to initial segments like this. So this is W in this case. And then it happens that if we take the hereditarily ordinal definable sets from this W, just parameters are elements of W, right? Then it's a model of Zermelo-Frenkel in which the count of parameter-free choice fails. And of course, the set of reals in this model, well, it is a model of PA plus the negation of parameter-free choice. And by construction, it does not include cardinal collapse. All cardinals of L are presented. So in principle, we can define this model as a class in the second PA. So just to get the whole result, we need only the consistency of the second PA. Well, and correspondingly, there are two different models. That is first omega prime. We take now countable initial segments, which are not necessarily finitely high, but to the contrary, look, every bush in this forest, so to speak, has to be of finite height. That is, if alpha less than omega 1, then we consider all indices which begin with this alpha. So let's call it a bush from alpha. Then such a bush has to be of finite height. But this height depends on alpha. So totally, it can be countably high, of course. And omega prime prime is just collection of all well-founded initial segments. And corresponding models then exactly prove what we need. That is, in the prime case, we get a model of parameter-free choice, but not the full countable choice. And the prime-prime model, countable choice calls, but dependent choice files. Actually, this is based on very old Jensen counterexample. Jensen's old model of 1965, but it's just a reproduction of Jensen's model inside the arboreal Sachs generic extension. And reals of these models are accordingly models of corresponding extensions of second P. Well, to the conclusion. Four models are presented. One in which comprehension fails by means of coefficient. The other one, just that one which I considered in more detail. And three models I briefly considered in the end. Well, and I must say that once again, there is earlier defined model of number 5 kind in a paper by Vika, Friedman, and myself with a 512 counterexample, but on the base of more complicated techniques. And all these models, just final remark, do not involve cardinal colors. And they are manageable on the base of second piano or technically on the base of Submodel without the power reduction. Well, so what else? References. One of papers has already done quite recently in mathematics. It's free access. And second paper is in archive. Well, that's all. And I thank the organizers and thank you very much for interest for coming to my talk. Well, I am really delighted to just give the start to the seminar. Thank you very much.
Okay, thank you, Vladimir. Let's all thank our speaker. And let's open up for questions, and feel free to just unmute yourself and go ahead and ask. Okay. If there are no questions, I'll stop the recording, and we can thank our speaker again. And I will let me double check the schedule for next week before I stop. So next week we will have Alexei Myasnikov from Stevens Institute talking about first order classification and non-standard models.